Hello and welcome back. This video is dedicated to a very important reservoir engineering concept, waterflooding and well patterns. Let's start with some history. Since the early days of petroleum industry and until the 1940s, companies developed oil fields using depletion drive. That was not quite efficient as oil recovery usually was below 25%. Occasional natural water drive helped a bit there it was available, and for secondary recovery people injected air, sometimes mixed with other gases. They also used the so-called vacuum process. Then gas was literally sucked out of production wells, followed by oil. In late 1940s, the game changed, with massive introduction of waterflooding both on brown and on green fields. Currently, waterflooding is the most common and cost-efficient reservoir stimulation technique. It reduces the number of production wells, improves production rate per well, and cuts oil production costs. Depending on relative position of injection wells towards the oil pool, we distinguish between edge waterflooding, peripheral waterflooding, and intra-contour waterflooding. Sometimes, combination of various flooding types are used. For uniform fluid recovery, we need to keep a certain distance between wells. This distance is called well spacing. Well spacing is selected based on field geology, and the arrangement of well bottom holes determines the well pattern. But first, edge water flooding. It's good to have edged water that helps our reservoir in maintaining pressure and push oil towards the production wells. But it will work better if we help by injecting more water into the aquifer. We drill injection wells around the outer oil pool outline in the water zone, and that is called edged water flooding. Peripheral water flooding is a bit different, as we drill wells between the outer and the inner oil pool outlines, that is, in the oil water zone. This method is used for reservoirs with low permeability around the oil pool. Following the success of edge and peripheral water flooding experiments, reservoir engineers started elaborating these techniques and come up with intercontour water flooding concept. It is especially efficient on large fields. There are rows of injection wells cut them into many blocks. Then we deal with intercontour water flooding. The water is injected right into the oil-bearing zone. There exist various intercontour water flooding layouts. For example, rows or lines of injection wells can cut a field into separate areas. Such systems are often used on large fields with extensive oil water zones. These zones are separated from the main oil pool, and each one is developed independently. Medium and small fields can be cut crossways into several blocks, and this is called block or line water flooding. From the experience, engineers learned that efficient line water flooding systems have no more than 5 rows of production wells between 2 rows of injection wells. So they came up with 1 row, 3 row, and 5 row designs. Such development systems proved to be much more efficient compared to edge water flooding, both in technical and economic terms. As this system evolved, more water flooding designs appeared, such as selective water flooding. Its main idea is to place injection wells not according to some regular pattern, but in certain field areas, depending on geology and geometry of the oil pool. It is often combined with other water flooding systems, as it allows for focused extraction of oil from unswept areas. There is another type of selective water flooding, typically used on highly heterogeneous reservoirs. A regular pattern of wells is drilled, and all of them are initially regarded as production wells. Only after the wells have been tested and produced for a while, engineers decide which of them will be the most efficient injectors. This system allows for aggressive water flooding with good sweep efficiency. Sand to edge water flooding is the system that has injection wells in the top of the structure or close to it. If the field is large, this pattern can be combined with edge water flooding. Pattern waterflooding deals with a system of evenly distributed injection wells that cover the whole oil pool area. If we look closely at such system, we will see that it consists of many identical elements making a large pattern. Depending on the configuration of each element, recognize 4-spot, 5-spot, 7-spot, 9-spot, and line drive pattern. Please mind that there are normal and inverted patterns. A normal pattern element consists of one injector surrounded by several producers, while an inverted element has one producer instead. A pattern can also be regular or skewed, depending on geological properties. 5-spot pattern is the most common. It has the following characteristics. Injector-producer ratio is 1:1. The pattern element is a square. Well spacing is equal. Displacement efficiency is high. 7-spot pattern has the following characteristics. Injector-producer ratio of 2:1 for normal and 1:2 for inverted pattern. The pattern element is an equilateral triangle. This pattern is rare because of non-equal well spacing. It can be used for pilot waterflooding if we want to find out the water breakthrough direction. 9-spot pattern has the following characteristic. Injection to producer ratio of 3:1 for normal and 1:3 for inverted pattern. The pattern element is a square. This is the second most popular waterflooding pattern thanks to its high displacement efficiency. Line drive pattern has the following characteristic. Injector-producer ratio is 1:1. The pattern element is a rectangle for direct line drive or displaced row of injectors and producers for staggered line drive. In staggered line drive pattern, injectors and producers are displaced against each other by half the distance between wells of the same type. Staggered line drive is more efficient than the regular one. Please mind that both line drive and 5-spot pattern have 1:1 injector-producer ratio, which effectively means that the number of injection wells is equal to the number of producers. This ratio is very important in situations where either injectivity or productivity of the wells are limited. For example, if injectivity is less than productivity, then we want to use the 9-spot pattern with more production wells than injectors. We don't want to have too many injection wells as each of them brings extra expenses, so each oil barrel produced will cost us more. As you see, it is very important that we choose the optimum pattern for our field, and to do so, we need to study all information available. So, what are the major well pattern selection criteria? First, production facilities, including the number of wells, well productivity, and artificial lift, should be consistent with suggested field development scenario. But we should have enough facilities to handle planned injection and production rates. Then, our well pattern should account for reservoir features such as dip and isotropy fractures. Thus, if we know that in this region natural fractures are oriented from northeast to southwest, we need to arrange our well in a way that will prevent an early water breakthrough. In other words, fractures should not be directed from injectors to producers. If there are wells already in place, our pattern should include them. Finally, our well pattern should be in line with the lease agreement. If we follow these rules, we will end up with a pattern that will help us maximize both recovery factor and net present value of the project. Companies that develop gas and gas condensate fields use the following well patterns: regular triangular or rectangular pattern, line pattern, well located in the crestal part of the formation, irregular well arrangement. Regular well pattern are made up of multiplied triangles or squares, and wells are drilled in vertex point. If our reservoir is homogeneous, a regular well pattern will cause consistent drainage areas and production rates for each well, as well as uniform change in reservoir pressure. For reservoirs with heterogeneous reservoir properties, regular patterns are less advisable. Another drawback of such system is necessity to build intricate gas gathering system and intra-field communications. Line pattern is commonly used on gas condensate fields with pressure support system. Like on oil fields, on gas fields we inject water or gas. Line pattern is selected if reservoir geometry allows so. Unlike a regular pattern, it does not require a spider web of communications and pipelines. Putting wells in the crestal part of the formation, that is at the roof or the gas pool, is recommended if the reservoir is homogeneous and has good pressure support from a nearby aquifer. However, the most common strategy in gas and gas condensate field development is irregular well arrangement, that is, using no pattern whatsoever. There are technical and economic reasons for that. Irregular well placement is less costly in terms of both money and time, and needs more compact gas gathering system and communication network, which also cuts expenses. We are done with well pattern. In the next video, you will learn about reservoir simulation. See you!